Hi everyone, welcome to this week's online class, which is on data and process modeling. This week we're going to talk about data flow diagrams and process modeling concepts and tools. This involves the use of data dictionary and process descriptions. We're also going to talk about the symbols that are used in a data flow diagram and explain the rules for their use. We'll explain how to level and balance a set of data flow diagrams, how we can use a data dictionary, and what is the relationship between logical and physical models. So let's start off with the chapter slides. I will quickly skip over the first two set of slides because these are just the chapter objectives, and you can pause the video and read them yourself. So I'm skipping to slide number 4 directly. Here you have the definition for logical models and physical models. Now, this connects us back to the idea that we discussed early on in the semester about how important it is for a systems analyst to document everything, document all the requirements of the system. A logical model, which is essentially your data flow diagrams, help you show what the system must do regardless of how it will be implemented. So it helps you look at the flow of data in your system. What are the different processes that the data has to go through, and where, in which steps is the data stored? It does not necessarily touch upon how the system manages to do those processes. So it's more like a black box when it comes to processes, but it helps you understand the direction of the data flow and what the overall system looks like. System analysts use graphical techniques to describe an information system all the time. The reason for that is that graphs are easily understood. A system that involves IT processes can get complex very easily. So just documentation, which involves writing up all the steps, may take more time, and it also may be harder to understand. So graphs are an easy way to simplify the whole process and show a broad overview of what the data flow in your system looks like. A DFT uses various symbols to show how the system transforms input data into useful information, how the data moves through the system, but it does not necessarily show program logic or the processing steps. To see how the data flows managed and how it is stored is what we essentially use a DFT for. It shows what a system does, but it does not necessarily show how it does it. So at this level, in this layer, we are referring to processes as essentially a black box. Data flow diagrams can use symbols to show the different components of your system. On this picture or image that you see on the slide, these are the two most commonly used systems. We're going to follow the Gain and Sarson's system, although the Jordan one is also commonly used. But just for consistency, if you're using the Gain and Sarson system, then you have to consistently use this system, which is on the left-hand side. And if you're using the Jordan system, then make sure that you're using the Jordan symbols consistently throughout the semester. You can see that there are 4 basic symbols that are used in the DFDs. The first one represents processes. This is what the black box is when I was referring to earlier in the video. In this example, the process is to apply payment. We're not going to focus on how the payment is applied and what are the steps involved in applying the payment. We just want to show that this is the step where the payment is applied. Then we use an arrow to show the data flow. These arrows can be unidirectional, which means that the data is only flowing in one direction, or they can be bidirectional. But I would recommend using 2 arrows back and forth if you have a bidirectional data flow at any particular part of the system. The reason for that is it simplifies the diagram a little bit. And then you have data stores where data is temporarily stored while it goes through processes or while it waits for the new processes to be applied to it. And finally, we have an external entity. These are basically outside your system. You can also call them as actors because these are outside the system, but they're using the information or the data that is within the system. Customers could be these external entities, or employees could be these external entities. These would be the four symbols that you're going to use for your data flow diagrams. Let's take a closer look at the process symbol. This is the symbol that you're going to use to represent a process in your system diagram. A process symbol must have at least one input and one output. It contains the business logic that transforms the data, and the process name has to be a verb. So it essentially identifies the function that the process is going to perform. An example of that could be calculate commission or calculate discount or apply rent payment. We refer to this process symbol as a black box because, like I said earlier, we're not focusing on how the process is performed. Instead, we're only focusing on what the process does. Usually we have a number for the process that we are documenting. The number is just for identification reasons, and it also helps you get an idea about the level of the process. So for example, if it's a high level process, we can number it number 1, and then we explode it down into further steps or further processes as 1.1, 1.2, or 1.11, 1.12. The levels that you can go into depend on the process itself. So there can be multiple levels of a process, and essentially we break it down till the point where you cannot further break it down into simpler processes. So we explode the process into its functional levels, and the number describes what functional level we're referring to. This slide shows you a good example of what correct data flow diagrams look like in terms of the components of the data flow diagram. It represents one or more of these data items, and the symbol for data flow is a line with a single or double arrowhead. If it's a single arrowhead, it just represents that information is flowing in one direction, and if it's a double arrowhead, then it represents information going in both directions. But generally, I would recommend using 2 arrows in opposite directions if you're trying to represent a system which inputs data as well as outputs data. So for example, here, the first example is the process of creating invoice, which takes the input as services performed and it outputs the invoice. The second example here is grading student work. It takes the submitted work as an input and it outputs the graded work as well as the student grade. The same can go on for these other 2 processes. The third process takes 2 input values and outputs 1 value. And over here, the last one shows multiple processes in the same flow of data. When we are creating our DFDs, we have to make sure that the flow of data and the process combinations must be logical and they must be consistent. So for example, over here on the slide, you see 3 different examples, which are bad examples on how to do it. The first one, apply insurance premium, which is a process, is giving out output, but it does not take any input, which is not possible. In the second one, calculate gross pay is only taking inputs, but it does not show an output after the gross pay has been calculated. And finally, the third one shows an incorrect input, which is not sufficient to perform the process and output the final grade for the student. Inside these processes, like we earlier called them black holes, what goes on inside has not been elaborated at this step. It's going to be elaborated later down the line, but for now you can consider them to be black or gray holes depending on how descriptive the name of the process is. The name of the process has to be descriptive of what the process is doing, but it doesn't have to be too long, or it should not be a paragraph long. It should just be long enough for you to understand what this process essentially does. A data store symbol represents essentially where the data rests. So a DFT does not necessarily show the detailed contents of the data store. It does not show the specific elements or the structure of how the data is stored. It just shows that this is the rest area for your data. The elements and the structure of the data can later on be defined in a data dictionary. So for example, details like what is the first name of the customer, what is the last name of the customer, what is the address, zip code, cell phone number, the credit card associated with that customer. All of that information is going to be in your data dictionary and not in the DFT. So you can imagine that a data dictionary may become quite large because of all the detailed information that must be stored inside of it. A data store must also be connected to a process within a data flow. The reason for that is if it's not connected to a process with the data flow, then we don't really understand what the purpose of that data store is. So it has to be connected to a data flow and to a process. So where is the data in the data store coming from, or where is the data in the data store going to be used, and what are the different processes that are applied to a data store before it reaches the store, and what happens to it after it exits the store. Now here's an example of a part of a data flow diagram where you see the process that the data goes through. Then it's stored inside of a temporary data store, and then it is later exited into another process. In this top image over here, you see the correct examples of using this part of your data flow diagram, and at the bottom you see the incorrect examples, and you should not be following the incorrect way. The correct way is that a process is applied to your data. For example, let's take this third example over here where a patient comes to the hospital, fills out the admission form, and the patient's information is stored inside the patient's table. Then the data from there flows to another process where the patient is diagnosed or where the patient is treated. Now, the steps inside this process are not listed over here because that's not our main focus for now. We're just focusing on how the data is flowing through the system. And once the patient has been treated, the data from here goes back into the patient's table to update that, and from there it can exit and flow into, let's say, another process, which would be your healthcare insurance, or it could go into billing. So it can become quite complex even for a simple example. Over here in the incorrect ways of creating a data flow diagram, you see in this first one that data is flowing from a data store into a data store. That is not correct because there has to be a process in between through which the data passes and then gets to the new store. If there is no process between these two data stores, you're essentially creating a redundancy which could just overburden your system. So the data has to go logically through another process for it to be stored into another data store. So you get the idea here. Now let's look at the entity symbol, which is used in your DFTs. The entity symbol shows how the system interfaces with the outside world. These are external entities which absorb the data that came through the system, or they could also be external entities that are providing the data to our system. So a DFT shows only external entities that provide data to the system or receive an output from the system. These entities do not have to be a person specifically, so it's not necessary for the entity to be a customer per se. These entities could also be a bank, let's say, for example, where our data is coming from, so they're providing input data to us, or they could be where we are submitting our output to. DFT entities are also called terminators because they are either the origins of the data or they are the final data destinations. So by terminating, we're essentially saying that the system has done their job and this is the final destination for our data after all the processes have been performed on it. So for example, it could be a customer invoice. After we've submitted the customer invoice, the requirements of the system have been fulfilled and all the necessary processes have been undertaken for the customer to receive the final invoice. Each entity must be connected to a process by a data flow, because that essentially determines if the entity is an origin or if the entity is a final destination for the data. On this slide, you can see some nice examples of how the entity symbol is used within your data flow diagrams. So for example, at the top over here, you see the correct ways of using the entity symbol, and at the bottom, you see the incorrect ways. Let's look at the correct ways. So over here, the customer is an entity. The customer makes a payment, and the payment goes through a process of apply payment. Then over here, the entity, the bank, is the final destination. You create a process of preparing the deposit, which is then submitted to the bank. Or you could have a process which is a circle. Essentially, the customer places an order, it goes through the process of verifying the order, and then an invoice is sent back to the customer. The same goes for this example over here. A process creates the paycheck is submitted to the employee then submits the time card, and it goes back to create a paycheck. So what you can see is in these examples, the entity is either an origin of data or it's the destination for the data. In the incorrect parts of the slide, you see that an entity cannot directly be connected to another entity. The reason for that is we define the entities as being external elements, so they're not related to our system. So essentially, if it's two external entities connected to each other, it has nothing to do with our system, so we would not create this part of the data flow diagram. Over here, you see that it's a data entity is incorrectly connected to a data store. Now that's also not possible because for data to be stored in a data store, it has to go through a process. There should be a process symbol here which says that apply payment, and after the data goes through that process, only then it can be stored in a data store. The same goes for this example here, where it cannot go directly from a data store into an entity. There has to be a process which applies the payment, and then after it has been applied, it goes to the final entity, which is a bank. So far what we've looked at are some of the guidelines that we need to follow in order to draw a DFT. And as you can see from what we've covered so far, that the graphical model of the information system, which clearly tells you what the flow of data is, what are the processes, what is the sequence of the processes, it helps you understand the system better. So for example, if you're explaining it to a customer, it would be really easy for them to look at the DFT and understand how the data is flowing through the system. Or it could be extremely useful if you're explaining the process to a programmer. The programmer can easily see what are the ways in which the data is processed, which steps are the parts where the data is processed, and where does the data originate from, where does it go to. So the programmer now has enough information to start programming the system, because they have clear directions on where the data is flowing. So essentially, when you're creating a DFT, which is a graphical model of information systems, you have to first review a set of guidelines for drawing those DFTs, and then you learn how to apply those guidelines to create a set of DFTs using a 3-step process. So let's review some of the guidelines that we've already covered. As you can see over here, we already said that data can go from a process into the process. So for example, if one process is authenticating the customer's information, the other process could be to generate the credit limit for the customer. It is also okay for the process to be connected directly to an external entity. After the process, the information is either delivered to the entity, or the entity is the one that provides the data that goes into that process. And after a process, it can also go into a data store, or the process can collect data from the data store. What you cannot do is have an external entity connected to another external entity. As we discussed earlier, this is outside of our system, so we do not need to represent this. An external entity can also not directly be connected to a data store. The reason for that is that there has to be a process involved in between. And finally, data cannot flow from a data store to another store, because that just creates redundancy in the system. So on this slide, we have the set of guidelines for drawing DFTs. I would recommend that you pause the video over here and read through all of these guidelines, which will help you create your DFTs for the group assignment. Make sure that you're putting enough time to create a DFT which is easy to read, easy to understand. You're using unique names for each set of symbols. You're providing a reference number for each process, like I mentioned earlier. It can be sequential, 1, 2, 3, or if you're breaking down processes, then you would have to put that in your reference number to show that a certain process is sort of a subset of another process. So 1.1, 1.2, 1.3, so on. And you also have to ensure that the model is accurate, it's easy to understand, and it meets the needs of its users. So when you're creating a set of DFTs, the first step in creating the DFTs is to draw a context diagram. A context diagram is a very, very broad overview of what the system looks like and what are the external entities that are involved in the system. So over here, what you'll see is we only have one. In this particular example, we only have one process, which is the overall order system, and that's called process 0 because it is the system. We're creating an order system, and the order system is taking inputs and giving out data output to external entities like the warehouse, where orders are coming in from, the customer, which are placing the orders, and they're being invoiced, or they're making their payments. You have the sales rep, which are getting the commission from the order system, a bank deposit, accounting gets cash receipts entries. So this is a very high level view of the system. And in the next step, we're going to talk about breaking this system down or exploding the system into sub-processes. So what you can see in the next slide is that the context diagram is exploded, and initially when you had only one process here, which was the order system, the whole system that we're creating, it has been divided into 3 sub-processes. The first process is filling up the order, the second process is creating an invoice, and the third process is applying payment. Over here, so the numbers of the processes have been changed from 0 to 1, 2, and 3, depending on the sequence of the processes. Also, you'll see that in the context diagram, the external entities were all communicating with the order system. Now that we have broken down the order system process into sub-processes, different entities are going to be communicating with different processes. So the customer communicates with the fill order process, and the sales department is communicating with the apply payment process. You can use double-headed arrows if the system is using data that flows in both directions, although it might be simpler to just use single-headed arrows and then like draw another arrow from here to here, if that's also a possible data flow. So the context diagram that we saw in the earlier slide, you can consider that to be the parent diagram, and this one over here is the child diagram, and we keep exploding these processes till we get to the most functional level, and we know exactly what processes are going to take place for the system to complete its requirements. So step 3 is where we take those sub-processes from earlier and we break them down even further or decompose them into simpler steps till we get to the most functional primitive of the system. So in the previous example, what you saw was that we had 3 processes listed down after we created the context diagram. In the next step, we're specifically taking this one process, level 1 process, fill order, and we're decomposing that into further sub-levels. Over here, what you need to make sure is that you're creating levels for the whole processes. So for example, fill order was, I think it was fill order. Yeah, fill order was the first process, and we're breaking it down so that we know exactly what are the steps that go into filling the order. So it has been broken down into verify the order, prepare the rejection notice, assemble the order, and so on. Now you can further break down these levels as well as necessary until you get to the most functional, simplified, broken down level of the whole process. You can see that even a simple process can be broken down further and exploded into multiple sub-level processes. So the system can become quite complex in that way. But what you do need to keep in mind is that you're using levels which have already been shown in your previous versions of the diagram. So for example, over here in my previous slide, I had an apply payment process. I have to make sure that in my final DFT, this apply payment process is still there, and it has been further broken down into its sub-levels as necessary. You cannot simply invent or magically create processes in the middle and in the later steps of the process. You cannot simply terminate processes without showing later on how or where they're used. So there has to be a certain form of consistency throughout your process of creating a DFT. So this is an example of how the apply payment process, which was the third process in our system, has been exploded into its sub-levels. So the apply payment has been divided or broken down into its sub-levels of post payment, and this is also the part where we start using data stores more, because once you post the payment, it has to be temporarily saved into a daily payments table, which then can take the information to the prepare accounting inventory and to the deposit payment process. These processes can further be broken down into sub-processes, like I said earlier, to their most basic simplified version of the functions that the processes are performing. So after we've gone through a few examples on the guidelines of creating DFDs, we come to the second part of the chapter, which is on data dictionaries. A data dictionary, like I stated earlier, or a data repository is the central storehouse of information about the system's data, and it's used to collect, document, and organize specific facts about the system. It also describes all the elements in the data and the meaningful combinations of the data elements. So, for example, there's a term used a lot in databases which is called metadata. That means data about the data, and that's where the data dictionary comes into play, is because data dictionary is the place which stores the metadata. It stores all the elements of your data. So for example, if an analyst is creating a report on, let's say, customer invoices, then which tables should the analyst be looking at? Because a database can essentially be really big. So instead of going from table to search for that data, the analyst should be able to refer to the data dictionary, which tells you which tables are storing which information and what are the more meaningful combinations of those data elements. So it's extremely important to have a concise, complete, and clear data dictionary. It can also be created in Excel, so just like a DFD, you don't need to have access to, let's say, a tool like Visio. If you do, that's great, you can always use that. But if you don't, you can create DFDs in a simple Word document. You can create a data dictionary in a simple Excel sheet as well. Inside a data dictionary, you have data elements. Data elements are defined as the smallest piece of data that has meaning within the information system. These are also called fields. So for example, if you're referring to a database, then think of what all the fields are that the database is storing, and together combined, those fields create records. So an example for that would be a customer record. So the fields that could be a part of that customer record could be the customer's first name, last name, the customer's address, the customer's zip code, the customer's credit card number. All of these fields combined would create a record for that customer. These records are the meaningful combinations of related data elements that is included in the data flow, or it's stored inside of the data store. These are also called your data structures. So basically, this is an example of one element of your data dictionary where you're trying to document all the different elements inside of your system's database are. This is over here. You can either have a system which stores or takes these data element entries in this format, or you could just simply create a table in Excel where you're trying to show the same type of information, but in a more primitive way. So for example, the label of the data element is social security number. It is a data element. The alias is SSN. We're not going to put SSN directly in here as the label because it could also mean something else. So make sure you put the full form of any abbreviation that you're using, and the abbreviation has been stated in the alias as well. What are the values and meanings? Is there a default value? For this case, it's not. But for example, for dates, a lot of the times January 1st is set as the default value, what are the acceptable values within this data element, what is the length of the data that we're inputting, and which tables are, or which sources are we taking this data element from. So for example, this one is taken from the application form, so that if an analyst is creating a report with this information, they can go back to the application form to verify the SSN. What type of encryption are we using? So security, that this is going into your payroll document where it can be encrypted. If it is encrypted, what are the tables that are storing this information and what type of encryption is being used? So you get the idea that you have to basically include all of the details of all the data elements that are going to be a part of your system. One quick tip here that I'd like to give is you can simply Google examples of data dictionary and get an idea of how data dictionaries are structured and what are the type of information that go inside of data dictionaries, just to clarify a little bit more on how you can use it for your own group project as well. So you get an idea of how to structure your data dictionary and what are some of the essential elements of your data dictionary. I recommend that you pause the video over here and go through the next 3 or 4 slides, which basically elaborate on how you would document the data flows. It's the same idea as we discussed in the example earlier over here. So the same concept can be applied to documenting different parts of your data flow. So the description of the data flow, the alternate name, the origin, destination, record, volume. So previously you had created a graphical version of the data flow. Now you're going to document it inside your data dictionary, so that whoever uses the data dictionary knows what the data flow diagram does, what the description is, what are the different elements inside of your data flow diagram. You can also include information like when was it last edited, who was the person who last edited it, to provide even more information than what you have listed over here. So make sure that you go through the next few slides and read through all the different elements of documenting the data flows. Now coming to process description tools. Process description are documents that provide details of functional primitive, and they represent specific sets of processing steps and business logic. The tools that are used include structured English, decision tables, decision trees, if statements. So for example, if a customer's total number of hours entered is 40, then process their payroll in this way, or if it's less than 40, then process it in so and so way. So those are some of the ways that process description and some of the tools that the process description uses. And what we see nowadays a lot is an object-oriented development. We're going to talk about this later on in a subsequent chapter, but for now, think of an object as a part of your data system, which combines all the data and processes that act on data into the things called objects. So for example, a customer is an object, so all the attributes related to the customer are stored in that object. Here's an example of a process description tool. So the previous example that I gave just right now, that if an employee's hours are greater than 40, if it's true, then yes, do calculate overtime pay. If it's not true, then do something else. That's a typical if statement, which is used for process descriptions a lot. Most of these process description tools involve 3 logical structures, which is your sequence, selection, and an iteration process. So the sequence tells you what to do next, the selection tells you what part of the information to pick, and the iteration tells you how long should you be doing this, or when do you stop the loop and then move on to the next sequence, this next step in the sequence of your process. So for example, over here, if you've reached the end of the file, then yes, do this, terminate the process, or store the data in a data store, or send it to an entity. If no, then you can go back to the loop and redo some of the steps that are involved in the process itself. Now, another tool of process description is structured English. So these are some of the guidelines to use when you're using structured English to describe your process. Again, use only the three building blocks: the sequence, selection, and iteration, the looping process. Use indentation for readability. This is also one of the most commonly used programming tool as well, where you indent the next step in the process so that it's easier for the reader to see where a certain part of the process ends and where another part of the process starts. Indentation, and basically it helps you read the levels of the processes as well. So like we saw earlier, that you could have a process 1, and then process 1.1 would be a sub-process inside of process 1. You could put the sub-process in a separate line and indent it so that it can be seen that this is a process of the overall broader level of the process. Use limited vocabulary, standard terms used in the data dictionary, specific words that describe the processing rules. So essentially you're following most of the programming language tools here as well. Decision tables are another process description tool which show the logical structure and all the possible combinations of conditions and their resulting actions. So for example, when you go to an ATM machine and you put in your debit card inside of it, it asks you for a PIN. So when you enter your PIN correctly, it takes you on to the next screen. That can be represented, that whole process can be represented in a decision tree. So in case you do not enter your PIN correctly, it goes on into a loop of asking for your PIN again, and it will keep doing that for a couple of tries till eventually it blocks your card so to provide a security feature. So basically a decision table should list out all possible outcomes that need to be considered, and you have to make sure that you're not overlooking any of the possible outcomes, because if that happens, then whoever is the user of the system will be confused and wouldn't know what to do next, or the system would also not know what to do next. The number of rules doubles each time a condition is added. So for example, after adding my PIN number for my ATM, if it asks me for another prompt or another secret code, then that layer of rules creates more complexity into the system. You can have more than 2 possible outcomes for any action, and they're essentially the best way to describe a complex set of conditions, because they list down all possible outcomes and also tell you what should be done if a certain possible outcome is arrived at. So this is a good example to show the decision tables tool. I'll go through a couple of them over here. If it checks for the credit status, if it's okay, yes, it's true, and the product is in stock, yes, then the system accepts the order. If the credit status is okay, but the product is not in stock, then the system rejects the order. So what you see over here is that you have all possible combinations of the 2 conditions that are being imposed, and you have what the system is supposed to do when any of these possible options come up. So it just shows you how easily you can demonstrate what the different if statements, if else statements are being applied within a specific process. So in the next few slides, if you go through them by pausing the video in detail, it just shows you how the decision table explodes when you add additional conditions to the decision tree, and it walks you through a specific example of doing so. Here's another version of the decision table, but this is a more graphical version of the table. I think it's better than a decision table because graphs are easier to read. You're applying the same types of conditions and rules, and you can clearly see what the outcome of each of those rules are. Decision trees, you can think of them as the graphical representation of the decision table itself. It shows the logical structure in more of a horizontal format, and it resembles a tree because all these conditions, when they're exploded, they branch out just like tree branches. It provides the same results as decision trees, but in a slightly more different format and slightly more simple. So far, whatever we discussed, we talked about more of the logical model of the system that we're trying to develop, while structured analysis tools like the ones we discussed today are used to develop the logical model for a new IS system, but these tools can also be used while you're trying to come up with a physical model. A physical model shows the system's how the system's requirements are implemented. So take some time to go through the next couple of slides, which discusses the difference between logical and physical models, and read through the chapter summary so that the same concepts can be reiterated. Make sure that you read all the text that has been provided to you and all the resources that have been provided to you so that you get a complete picture of this week's module.